Have you ever stopped and wondered how a machine actually learns? Today, we're going to pull back the curtain on one of the most important processes in all of artificial intelligence, model training. So, let's dive right in.
I mean, seriously, think about it. How does your email inbox just know what's junk? Or how does your phone unlock just by looking at your face? The secret sauce behind all of that is a process called machine learning model training. It's pretty much the engine that powers all the AI we use every single day. Okay, so let's start with the big question. What is model training? At its heart, you can think of it as a really advanced way of teaching a computer. But instead of a classroom, its textbook is made of data. And I mean a ton of data.
Now, the really cool part here is that we aren't programming a bunch of if-then rules. Instead, we give an algorithm a massive data set and just let it discover the patterns all by itself. The whole goal is to create a final model that can look at new, unfamiliar information and make incredibly accurate predictions.
Honestly, this is the best way to think about it. Imagine the algorithm as a student. The giant data set we feed it, that's its textbook. It's going to study that textbook, learn all the connections, and figure out how things relate. And then, later, we're going to hit it with a final exam to see if it actually learned the concepts or if it just memorized the answers.
And, just like in school, there are different teaching styles. First, you've got supervised learning. This is like giving our student a textbook that already has all the answers in the back. For that spam filter, it means every single email is already labeled spam or not spam. The algorithm makes a guess, checks the answer, and learns from its mistakes. Then you have unsupervised learning, which is way more like exploring. It's like we give it a giant, messy pile of photos with no labels and just say, go find some interesting groups in here. It has to find the patterns all on its own.
So we're spending all this time teaching these algorithms, but why is this training phase so important? Well, because this is where the magic really happens. This is the moment when raw data gets transformed into a genuinely powerful tool that can have a huge real-world impact. We're talking about everything from diagnosing diseases to powering a self-driving car.
High accuracy. That's the dream, right? Getting a model to be this good is the whole point. A model's performance in training directly tells you how well it's going to work out in the wild. A poorly trained model is basically useless, but a really well-trained one can do some absolutely incredible things. And this quote just hits the nail on the head. You can't quiz the student on the exact same questions from the textbook they just studied. That's not learning, that's just memorization. The real test, the only way you know if they've truly learned, is to test them on brand new problems they've never ever seen before. In machine learning, this is the difference between a model that just seems smart and one that actually is.
So how do data scientists actually pull this off? It's not just a matter of clicking a big go button. It is a very systematic step-by-step process, all designed to build the best possible model for the job. So let's walk through it. Here's the roadmap. It all kicks off with preparing and splitting up the data. From there, you pick out a few contender algorithms, fine-tune their settings, and then finally, you train them all and evaluate them to see who the winner is. Let's take a closer look at a couple of these steps. Okay, this step goes right back to our textbook and final exam idea. We take our whole data set and slice off a piece, usually about 20%, and we lock it away. That's our test set, the final exam questions the model never gets to see while it's studying. The other 80% is the training set, which is the textbook it gets to learn from. This split is so important for preventing overfitting, which is really just a fancy term for when the model cheats by memorizing the answers instead of learning the concepts.
Now, once the data is all split up, the data scientist has to set some ground rules. These are called hyperparameters. Sounds a little technical, I know, but think of them as the study strategy for the algorithm. It's like telling it how many times to review the material, or how complex its notes are allowed to be. These aren't things the model learns from the data itself. They're the rules of the game that are set in advance to guide the whole process.
And this brings up a really key point. There's no single best algorithm for every problem out there. Data scientists kind of have to act like detectives. They look at all the evidence, the size of the data, the speed they need, the number of features, and from there they select a handful of candidate algorithms that are the most likely to get the job done right. So we've prepped our data, we've chosen our candidate algorithms, and we've set all the rules. Now it is time for the main event, the final competition to see which model truly comes out on top.
A perfect way to think about this is like a track meet. You don't just have one runner. You've got multiple algorithms competing, each with slightly different settings. You can think of those as different running shoes or strategies. They all compete in these trial heats, and only the absolute best performers get to advance to the final championship race.
And in that final race, the top models are finally let loose on that unseen test data, the final exam. Now this is where it gets really interesting, because the winner isn't always the one with the highest accuracy score. Look at algorithm B here, 98% accurate. That's amazing, but it's slow. For a medical diagnosis model, you probably want that 98% accuracy no matter what. But for a real-time movie recommendation engine, that slowness makes it totally useless. In that case, algorithm C, with slightly lower accuracy but much better speed, is the real champion. It's all about finding the right trade-off for the specific problem you're trying to solve.
So, at the end of the day, the champion model is the one that proves it actually learned the material, not just memorized it. It performs well on the textbook examples, it aces the final exam with brand new questions, and most importantly, it actually solves the real-world problem we set out to tackle in the first place.
And that pretty much brings us to the end. We've seen that training in AI is a whole lot like teaching a student. It takes good study material, the right teaching style, and a fair final exam. Which kind of leaves us with one last thing to think about. As these AI students get smarter and more capable, what's the next critical subject we should be teaching them to help solve the world's biggest problems? Something to chew on. Thanks for watching.